Guys! I made a lamp turn on with a button. I think I'm an engineer now. Okay, a 5 years old can do that. Yeah, but can a 5 years old explain why it turns on? Okay, fine. That's actually a good question. Welcome back to the channel. Today we're kicking off a 3-part series on something that looks stupidly simple. A toggle switch controlling a lamp. But by the end of these 3 videos, you'll understand how controls engineers actually think, not just how to make things work, but why we build logic the way we do. We're using Codesys, writing in ladder logic, and by part 3, we're having a blinking LED that would honestly look at home on a real machine. Let's begin at the beginning. Wait, is that a real question? Because obviously we need buttons to turn stuff on. Think bigger, mad guy. A toggle switch isn't just hardware. It's the translation layer between a human and a machine. Oh, so it's about operator intent. Exactly. When an operator presses a button, they're saying, I want this state to change. Your job as a controls engineer is to capture that intent reliably, no matter how they press it. So the toggle sits right in the middle. It's manual. A human has to act, but it's also structured. The machine responds in a predictable way. And predictability, that's the entire foundation of industrial control. Before we touch any code, let's look at the real thing. A push button has 3 key terminals you need to know. Normally open, NO, no connection until you press. Normally closed, NC, connected until you press. And common, COM, the shared terminal. And push buttons come in 2 flavors you need to respect. Momentary and maintained. Momentary equals spring-loaded, returns to rest when you let go. Maintained equals stays where you left it. This distinction will matter a lot in part 2. File it away. Okay, before we open Codesys, we need to talk about something nobody explained to me properly when I started. Ladder logic has its own alphabet. If you don't know it, the code looks like hieroglyphics. It's called ladder for a reason. 2 vertical rails, and between them, rungs. Each rung is 1 piece of logic. Left rail equals power. Right rail equals ground. Logic flows left to right. Symbol number 1, the normally open contact. 2 little vertical bars. It's an input check. It asks, is this signal true? If yes, current passes. If no, it blocks. Like a door that's closed by default. You need true to open it. Symbol number 2, the normally closed contact. Same shape with a slash. Opposite behavior. It asks, is this signal false? If yes, current passes. A door opened by default. True closes it. Wait. So normally open contact equals true passes? Normally closed contact equals false passes? Yes. And this trips up every beginner. Write it down, tattoo it on your arm, do what you need to do, but you need to remember these fundamentals. Symbol number 3, the output coil, goes at the end of a rung. If current reaches it, the output becomes true. This is what actually does something. Turns on the lamp, starts a motor, opens a valve. And the little teaser, the set coil and reset coil. A normal coil is true only while the rung is energized. A set coil latches, stays true even if the rung turns off. A reset coil forces it back to false. That's how we build memory. And memory is how we build toggles. But that's part 2. Master this 5 and 80% of ladder logic is already readable to you. Okay, now we can open Codesys. Here's our program. Toggle BP. Before any logic, we declare our variables. Watch what type I'm using. BOOL, not int, not real. BOOL. And this is where a lot of beginners mess up. Why does it matter? A button is just 1 or 0, right? An int can hold that. It can. But ask yourself, what are the valid states of a push button? Pressed or not pressed? 2 states. So your data type should represent exactly 2 states, nothing more. If you use an int, suddenly you have to ask, is 1 pressed? What about 2? What about -1? You've invented ambiguity where none existed. And real is even worse. Floating point rounding on a button? No thanks. Golden rule, continuous values, go to the real. Discrete states, go to BOOL. Your lamp is discrete. Your button is discrete. BOOL. All the way through. Here's the simplest possible toggle. 1 rung, 1 normally open contact, 1 output coil. Press the button, start BP becomes true. Current flows through the normally open contact, reaches lamp 1, lamp turns on, release the button, start BP becomes false, contact blocks, lamp 1 turns off. Done! Lamp works! Ship it! Mad guy. What happens when you let go of the button? The lamp turns off, so the lamp only stays on while you're holding the button. Oh, that's not really a toggle, is it? No, that's direct control. Also called level-based logic. The output mirrors the input. Useful sometimes, but it's not what we want when we say toggle. What we've built is technically working, but it's the most basic version possible. And that's okay. You need to understand the basic version before you can appreciate why we need something smarter. Now, this is where my maintenance background kicks in. Let me tell you what I've seen in real factories. Operators don't press buttons the way engineers imagine. They press too fast. They press too slow. They lean on buttons while talking. They hit them with elbows, gloves, tools. Sometimes they press twice because they are not sure it registered. And if your logic depends on a perfect press, your machine will betray you at 3 a.m. on a Saturday shift. Controls engineering isn't about clean conditions. It's about human proving your logic. Writing code that works when the world is messy. This is the mindset shift. You're not coding for perfect conditions. You're coding for tired operators, faulty wiring, and mid-cycle restarts. Let's lock it in. Today we covered why toggle switches exist, operator intent, normally open, normally closed, common, the electrical reality, momentary versus maintained buttons, the 5 core symbols of ladder logic, why we use BOOL for discrete states, the direct on and off rung and its limitation, the maintenance mindset, human-proof logic. And in part 2, we fix the problem, the big problem. 1 press to turn on, another press to turn off. For real this time. That's where memory, edge detection, and state verification come in. It gets good. If this made sense to you, even a little, you're already thinking like a controls engineer. And if it didn't, drop a comment. I read every single one of them. Tell me, what's your background? Maintenance? Electrical? Student? Total beginner? I want to know who's on this journey with us. Subscribe so part 2 doesn't get lost in the algorithm void. Bye-bye!